So in the last lecture we had a peek into neural networks. We saw how in a neural network we can train the network by presenting it with the sample training data, and for each data we observe the output of the network and compare that with the golden output, because it's a supervised learning system. And when we compare the output of the neural network with the golden output and compute the error, then we learned a mechanism for propagating that error back into the weights of the network and modify the weights of the network in a way that the overall error decreases. And we also understood an important concept, that we have a learning rate which adjusts the weights in a way that the overall combined error of all the samples, they converge to a local minima, and we don't make any drastic changes in the weight, because then that would completely take it away from it would become good for some samples and become quite bad for other samples. So therefore it makes sense to modify the weights gradually and slowly converge into the local minima using the backpropagation algorithm, which is a way of using gradient descent for updating the weights. In this lecture we will take a peek into two of the most popular types of learning networks or networks in terms of their structure and in terms of the type of functions that they attempt to model. Namely, we are going to look at convolutional neural networks, which are popularly known as CNNs, and recurrent neural networks, which are RNNs. They are variants of the generic structure of the network, targeting different types of applications, as we shall see. And later on we are also going to discuss some of the other types of networks or derivatives that have come out of CNNs and RNNs. If we look at the types of neural networks broadly, then the most popular type is what is called the feed-forward network, in which, as we saw in the last class, we have an input layer and an output layer and one or more intermediate layers. Now, if the number of layers between the input and output layer is greater than 1, then we call it a deep neural network. And the subject of learning functions using deep neural networks is broadly referred to as the deep learning exercise. If it is not a feed-forward network purely, and that is, I have feedback from a layer to some layer to some previous layer, then we call it a recurrent neural network. So in this picture you can see that in the recurrent network we have the feedback from the layer 3, in this case, back to the layer 2. So then we call it a recurrent neural network. We shall see that in general there are various types of structures for recurrent neural network and suitable for certain types of applications. The activation functions are also can be of various types, and there is a small table here which shows some of the activation functions. For example, identity is a very simple activation function. Then we have sigmoid, we have the tan hyperbolic function, or we may have the step function, etc., etc. And there are others like ReLU and others which are used in various contexts from various perspectives, ranging from the type of functions that they can model, or even from the perspective of verifiability of the neural networks. There is one type of network which we may not have the time to really get into, are called Boltzmann machines, and the one that you see at the bottom with which is symmetric and RBM. These are Boltzmann machines. As opposed to a feed-forward network, a Boltzmann machine may have activation flowing in both directions. So if you have these two layers here, as you can see, the ones with the Xi's and the one with the HI's, then activation for the HI's depends on the values of the Xi's, and also the activation of the Xi's depend on the value of the HI's. So they are symmetric in the sense that the activation can have the influence in both directions, from the left to the right as well as from the right to the left. Boltzmann machines also compute by using methods like relaxation and settling down into a set of weight values, and they are widely used in different kinds of optimization problems. We may do one or two during the tutorials, but I don't think that we'll have the time to do the theory behind Boltzmann machines here. So let's move on. We first start looking at convolutional neural networks. So to understand that, we need to understand what is convolution. So let's start with that. Let me move into full screen. So let's first understand what is the convolution function. So some of you may have already studied convolution in mathematics, but nevertheless let us understand it by taking a simple example. So suppose we are tracking the location of a spaceship with a laser sensor. So if I look at time in this direction, and let's say the location is in this direction, suppose at some point of time the spaceship is here, at some point of time it is here, some point of time is here. Now we are sensing the location of the spaceship with a laser sensor. So it produces a single output xt, the position of the spaceship at time t. So I have this function which senses the position of the spacecraft, and it produces at time t the position as a function of time. Now suppose the laser sensor is somewhat noisy, and therefore we wish to take the average of multiple measurements. So now if we think of this as a discrete set of samples, then it means that if I look at the samples which are coming, then I get some sample at time t, then I get a sample at time t plus 1, then I get a sample at time t plus 2, etc., etc. And we are told that the positions are not exact because there is some amount of noise in the sensor. So we wish to take the average of the multiple measurements. So if we get some value xt here, and I get some value of xt plus 1 here, and I get some value xt plus 2 here. Now I could just take the average of them. So I could do something like sigma over xt, and then divided by the number of samples that I have. The problem here would be that the spaceship is actually moving. So as it moves, if I look at local values, maybe over 3 consecutive samples, then the spaceship may not have moved significantly within that time. But suddenly if I compare this position with, say, x of some t minus, let's say, delta, and delta is reasonably large, then obviously the position of the spaceship in that amount of past and its present position are actually quite different. So if I include that also in this summation and average, then the output that I get, that is this value, is not going to be very accurate in terms of the position of the spaceship. So given that it is moving away, so I should not take the same weightage of the samples which are recent and samples which are taken from the past. So therefore I use what is called a weighting function. So and in the weighting function WA, the weighting function WA that you see here, that is a function which will ensure that if I look at x of t minus delta, where delta is large, then the corresponding W will be very small, so that this term will have negligible influence on the present position of the spacecraft. So in a continuous domain, if my time is continuous, then I would get something like this. That is the convolution of the readings that I get, that is x, and the weighting function is defined as something like this, and here I may vary this from minus infinity to infinity. So this operation is called the convolution. The first argument x is called the input, and the second argument W, which we have constructed in a way to suit our requirements, is called the kernel. Later we shall see that convolution is a commutative operation, so we shall see that this is the same as W convolution x t. So it's commutative. This operation is commutative. But nevertheless, we make a distinction between the input and the kernel, because the input is what is coming from the outside. They are the samples, they constitute the input data, and W, the kernel, is something that we construct to have the desired effect on what we want to learn or what we want to do with the convolution computation. If you look at the discrete case, which is the case which we discussed just now, where you have discrete samples of the data, then we define the convolution operator in a similar way. That is, the convolution of x and W gives me this one, where for each of these values of A we have a sample. So the samples are spread on the timeline. These are discrete samples, so I have from minus infinity all the way to plus infinity, and I have all these samples, and well, if this is my current time t, then I am looking at all these samples, the x at t minus some delta, t minus 2 delta, etc., and also t plus delta, t plus 2 delta. Now in time, obviously it does not make sense to use samples from the future unless you already have the data pre-generated, which is sometimes the case. Sometimes we get time series data and we want to estimate the state of the system at particular instances of time, and there we may use also data available from the future, but in general when we deal with time, we are only looking at the past if it is online. But in other domains, like we shall see for image processing, etc., we can have samples from both the past of t as well as in the future of t, and t may not always represent time. It can be just any integer, and it may also represent position, for example, in a two-dimensional image. So then this is the definition of the convolutional operator. can also be defined over more than one axis at a time. For example, if we talk about a two-dimensional image I as our input, and the ij represents a pixel in the image, then I can define a convolutional operator over the pixels of the image. So what it means here is that in my image I have a pixel somewhere here, and then if I say that this is ij, if this one say is the ijth pixel, then I have a pixel which is I minus 1j, I have a pixel which is I plus 1j, I have a pixel which is ij plus 1, I have a pixel which is ij minus 1, I have a pixel which is I plus 1 j plus 1. So there are many pixels around it, and I may want to compute some function for this pixel, the pixel at the middle, which is of our interest, and I may compute some functions by looking at the neighboring pixels around it, right? And then for the other pixels, my kernel is such that for the other pixels they don't have a contribution, that is, the w value will become 0, so they will not be able to contribute to anything. But there is some kind of convolution that we compute over these pixels to get some value out of it, which may be useful in certain contexts. So we shall see some of those kernels that we can design for performing various kind of image processing applications. So the two-dimensional convolution is again defined in this way, that is, I have imn times k of I minus m j minus n. This is the two-dimensional convolution, and as I noted previously, I can replace m by I minus m. So I write this as I minus m, and n by j minus n, so I write this as j minus n. And then if I replace this I by I minus m, if I replace m by I minus m, so if I replace this with I minus m, then effectively it will become m, and if I replace n by j minus n, then this will become n. So effectively what I'll get is the same thing. So that means that again the convolutional operator is commutative, so I can the function that I get through this and the function that I get through this, they are the same function, as you can see here. It's just replacing the variables by different names. So here are some interesting kernels that we could use on a image to come up with interesting things. So let me explain what this means. So I have an image, okay. From that I take a 3 by 3 set of pixels. So if I blow this up, this is going to look like a 3 by 3 by 3 set of pixels. Now what I do is I compute the convolution of this with this as the kernel. So this is my kernel. This is one of my kernels. Now if I compute the convolution of this 3 by 3 set of pixels with this kernel, I will get some value. That value becomes the value of the middle pixel. That is, whatever I find through this function, that becomes the value of this middle pixel. So that's what we get here. And now you can slide this 3 by 3 window over all parts of the image. So if I look at the image like this, I take the 3 by 3 like this, then I take 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 3 by 3 like this. So I take all possible 3 by 3 combinations, and for each of them I replace the pixel at the middle with the convolution of the kernel with these 3 by 3 pixels. If you do that, then you will get the corresponding picture as a consequence. So the first one, the first kernel that you see is the identity, which means that you can try this out for yourself. If you take the convolution of this, which just has the central pixel as 1 and all the other pixels are 0, then what exactly will happen is that whatever the 3 into 3 that you took, for the 3 into 3 that you took, so out of these 3, then this 3 and this 3, it is only this one which will have a non-zero coefficient 1. So effectively, if you take the convolution of this with this, all that will happen is that this pixel value will remain the same, it will not change. So that's why it's the identity convolution. And if you take the identity convolution with the 3 by 3, you get exactly this picture. So this is the original picture, and by taking the convolution with the identity, it doesn't change, so you get the same one. Now there are, for edge detection, one may choose to use a kernel like this or like this or like this, and you can see for the same image, if instead of taking the convolution with the identity, which leaves it as it is, if I took the convolution with say this kernel or this kernel or this kernel, then we get these as the corresponding images. Now as you can see, in the third of these, you will start seeing the contours of the face of the animal, whereas these are too dark, you don't see anything here at all. So we then learn that by using the convolution with this kernel, I get to something which is kind of close enough. Now remember that these are the weight values, because the kernel is nothing but actually producing the weight values. And if I take the input values, namely these pixels as the input, every 3 by 3 block as the input, and then when I take the convolution of this, it's like a small subset of the neural network where I am weighting those pixels with these coefficients and then summing them up. So that's what is happening. I have the input layer, and then the input layer, for the input layer I am taking every 3 by 3 pixel, and then I have this network which is computing the convolution, and it's producing the pixel value for the middle pixel, right? Now that is then, if I take this for all the 3 by 3, then I get a reconstructed image here where I have only these contours, that is only the edges. Now there may be something that I am trying to detect which is not easy to detect when you have a pixel with so many different colors and so many different grayscale and RGB values. So I use this kind of a filter to first convert it into an image which has the necessary features, and then based on those features my neural network will try to learn something or try to identify whether this is a horse, this is a llama, or this is a meerkat. I have some more kernels here. For example, this leads to sharpening of the image. As you compare this one, the original, with this, you can see it has sharpened it. And then this one is a kernel which blurs it. So if you compare this with this, then this is blurred. And we can have other blurring functions also, like a Gaussian blur will get me to something like this. Now we can use machine learning or the backpropagation learning that we saw to kind of learn these values of the weights, which gives me for a particular image the best kind of sharpening or blurring or edge detection, whatever, and then based on that we may be able to use other layers to then recognize what that image consists of. So if the kernel width is small, then the network will be sparse. What do we mean by that? So if we look at the type of network that we saw in the previous lecture, we were having what is called a fully connected network. So I have my input layer, then I have the next layer, and they are completely connected, which means every neuron here is connected to every entity in the previous layer. Okay. This is completely connected. And then I have another layer. Again, I have a complete connection. So then this is a completely connected network. Whereas, as we saw just now, when we are computing the convolution, so let's go back to the image that we were looking at. So if I take, say, this 3 by 3, then this 3 by 3, they are feeding into 1. So this node has connections to this 3 by 3. If you take another 3 by 3, then they are connected to another one. And of course there can be overlapping 3 by 3s. So there may be some, so it's not the case that each pixel is feeding to only one of them, but I can have some connection like this. But if you look at this neuron, it does not have any edge from here to any of these 3 by 3s. So there are, if I look at the second layer, then not all the elements of the first layer, they are all not connected to every node here. Maybe this is connected to these 3, this one is connected to these 3, this one is connected to these 3, and so on and so forth. Right? Now, if the kernel width is small, that means that I am dealing with a small subset of the inputs or the previous layer, then the network will be sparse. So for example, here the kernel width is 3. So I am just taking 3 of them and they are feeding into a node of the next layer. If you compare that with the fully connected network, each node here is connected to only 3 from the previous layer, but in a completely connected one, it will be connected to all of them. So then that will be much more dense. Okay. And similarly for cases where a node is feeding into only a subset of the nodes in the next layer, as opposed to a node feeding into all neurons of the next layer. Okay, there was a picture which I wanted. Where did that picture go? I can't find that now. Let me do one thing. Just give me one moment, please. Okay, let me do one thing. Let me show you something here. Okay, so here is, let's say, my input layer. And in this input layer, I have taken some k by k subset and then brought that out using a convolution. Now I can do this for various such this thing. Now there may be something that I want to detect in this. I may want to detect something in here. So let's say I want to find out whether this particular image has, let's say, the letter 5 written somewhere. Okay. Now what may happen is that in my image I may have a 5 written like this, or a 5 written like this, or a 5 written like this. So it may be in any orientation. It may also be written in different ways, like somebody wrote a 5 like this, somebody wrote a 5 like this, and so on and so forth. Now obviously if I want to detect this, if I want to detect these 5s, so let me take just one example rather than taking all of them. Let's see, in my image I have, let's say, 5 written like this. Now when I take this one, I may feed this into different types of, use different types of kernels. So maybe one kernel which tries to see that in its vanilla form, in this form, whether it matches with a 5. There may be another one. So here the 5 is still like this. There is another one. I feed this again to another one, where the 5 is written like this. So what I mean here is that I have various kernels which can take a 5 like take a 5 which is written like this and then flip it around to get one 5 like this. I can get another 5 like this, maybe I can get another 5 like this, and so on and so forth, and then recognizes each of these as a 5, right? Now in this case, the one which will recognize the 5 is the one which is trained with this orientation. So then out of the different blocks that we see in the next layer, one of them will say, hey, I have seen a 5. I can see a 5. So in this case, this fellow will say I can see a 5. This fellow will say no, I don't see a 5. This fellow will say I don't see a 5. So now we need to aggregate what we get out of these into another function which tells me did any of them see a 5. So to do that, we use what is called pooling. So you can use a type of layer which does the pooling. So let's go back to the presentation and let's take a look at that. So here we have this pooling layer. So for example, in this case, wait, just let me bring it into full screen. So as I said, let's suppose your image has this, then this fellow will say that I see a 5 because it is trained to see the 5 in this orientation. This fellow will say I don't see a 5, this fellow will say I don't see a 5. So the activation will come out from this in high amount. The activation for these will not be very significant. Now if we put a pooling layer here which kind of collects whatever it gets from the 3 and takes say for example takes a max of the activations, then it will say yes, I detect a 5 is detected. And in this case, in the second one, that is the one that we see here, the 5's orientation is like this. So it is then this fellow which says that I detect a 5, so it is going to give high activation. These ones will give low activation, and I will get in the pooling layer I will get a yes. Now on the other hand, if I got something like this, for example, if I fed it to this, then this fellow will say that I don't see a 5, this fellow will say I don't see a 5, this fellow will say I don't see a 5. So then the pooling layer will report that, well, no 5 was seen. So that means that regardless of the orientation, this thing that we see here, this thing is not a 5. Well, let's now move into the notion of recurrent and recursive networks. Now in what we saw so far, we were essentially doing the following. So let me again use some of the white space here to explain. My pen keeps on disappearing. So what we were doing so far is in convolutional neural networks, we are looking at, let's say, one layer, and so in the next layer, some of these are feeding to some of the neurons in the next layer. So maybe something like this. So we get a much more sparse network as opposed to a fully connected network. Now when we talk about a recurrent system, like a system which evolves over time, then I will have these inputs coming in as a time series. and there could be influences of the immediate samples, like we saw for the example on the spacecraft or location of the spacecraft. Immediate observations may have an influence on this, and also in some cases distant things may also have an influence on this. Okay. Now when we talk about recurrent networks, we try to deal with data which is sequential in nature and where the system is performing a recurrent function. The standard case where we see recurrence is when we are trying to model a dynamical system. So in a dynamical system like a control system, we have two entities. One entity which we call the controller, and we have the entity being controlled, which is the plant. So for example, in an automobile, the braking system consists of the actual brake shoes, etc., which forms the plant, and the controller is the software which is deciding how to brake the car. For example, in an anti-lock braking system, I may apply the brake in a way that the car does not skid, or that is, I don't have slip between the wheel and the ground. So they interact with each other, and I can think of the entire function that this is going through as a function over time. So if x is my state vector, if x is my state, and it consists of some c1, c2 to ck, which are my control variables, and let's say my p1 to pm, which are my plant variables. So if I look at the system as a whole, these are the variables which are updated by the controller, these are the variables which are updated by the plant as they evolve, and the state is the combination of this. Additionally, of course, within this c1 to ck, there may be some memory that the controller keeps for itself, and the plant may also have memory. For example, you know that many systems have things like hysteresis, where they actually remember some internal aspects of the state which may not be visible to the outside. So we have in the set of variables that constitute a state, and that is my x. Now the system evolution can be thought of as the values of x at time t, and then it evolves to the values of x at time t plus 1, then the values of x at time t plus 2, and so on and so forth. Now what brings about this transition from xt to xt plus 1 and from xt plus 1 to xt plus 2 is what we may call a transfer function. So it's the transfer function. It tells us xt plus 1 as some function of xt. So this is the dynamics. This is the dynamics of the system. This could be, for example, in a time varying system, it could be a set of differential equations over the variables in x, which defines that as they evolve with time, how do those variables change. Now what we want to do is we want to learn this f. We are given these data points, we know xt, we know xt plus 1, we know xt plus 2, and we are given many such time series data. So for one evolution, for another evolution, so many time series data, each having these xt, xt plus 1, xt plus 2, etc. as a time series. So I have many such instances, and based on this data I want to learn the function which will then be able to predict the value of xt plus 1 given my present state xt. Okay? This is what we want to do. So recurrent neural networks are a family of neural networks for processing sequential data, as I just now mentioned. They can scale to much longer sequences than would be practical for networks without sequence-based specification. So what does that mean? That means that if I did not try to learn this transfer function, and if I just try to learn the history, then there are so many possible variations that can take place that I would end up requiring a very big network. So most recurrent networks can also process sequences of variable length. So and they're used in a wide variety of contexts, not only just for the dynamical systems that we talked about, but also, for example, in NLP, where in a sentence you have different words at different positions, and the semantic interpretation of the sentence or even predicting a missing word in the sentence can be done by using a recurrent neural network, because it learns these sequences, and sentences are actually sequences of words. The key idea behind recurrent neural networks is that is the parameter sharing. So when we talk about a transfer function, the transfer function parameters do not change with time. So if you look at a control function, then the control function coefficients in the transfer function, they remain the same. So if we can learn them, then we can recursively use the transfer function to be able to predict the value of the state at the next time step or the next to next time step, and so on and so forth. And believe me, there is a whole body of research which is going on in an area called model predictive control, where you learn the model from the data and then you use the model that you learn in this way to predict that in what way your control system is going to behave, and appropriately, depending on the changes in the input, you can learn how to adapt the control so that it gives you the best performance. How do we handle the recurrent neural network? So let's see. So let's consider a dynamical system where, as I said, that f is the transfer function which takes the present state or the st minus 1, the previous state, and gives me the value of the present state as a function of the previous state. And theta is the set of parameters of f, which is what we will aim to learn by using the network. So the state after a finite number of steps can be obtained by applying the definition recursively. For example, after 3 steps I get something like this, that is, I apply so the state after 3 cycles is f of the state after 2 cycles, which is f of the state after 1 cycle, and so on and so forth. So that way I can repeatedly or recursively use the transfer function to deduce or predict my state after a certain finite number of steps. For a dynamical system driven by an external input signal xt, we also have the input as part of the state, because that can influence the output. So then we have st as a function of the present state or the previous state, if you may call st minus 1, and the present input and the parameters. So this represents my current state, this represents my current input, that is the input in this particular time t, and this is the set of parameters, and then this gives me the state to which I am migrating in the tth time step. So in the tth time step I am migrating from st minus 1 to st, based on this transfer function. Now let's see how does the structure of a recurrent neural network look like. So I have here the input layer. The input layer here is x, and then I have this hidden layer h, and with h I have this some kind of memory that I am allowed to keep. So some kind of memory is kept here, and this is feeding back into h in the next cycle. So if I unfold this out, so whatever is being stored here, that is being fed back into the network in the next cycle. So you can think of this as a register or something like that. So I can unfold this network over time, and then it's going to look like this, that I have xt minus 1 which is feeding into this layer, this is then feeding into this, and this is then feeding into this in the next layer, and so on and so forth. I could potentially open this up as a multi-layer network, and then I may compare this output O with my golden output O star, and then compute the error that I see in this. So what I am essentially trying to do, if you can see here, is that I am essentially, based on my previous state and my present state, I am predicting the next state, and I compute the actual next state. When I observe it, I find out what is the difference between that and this, and then I can take the square of this error and then use the back propagation learning algorithm that you saw to propagate the weights back here. But the thing to be noted here is that these are not separate edges. They are the same edge unfolded over time. So therefore, when we are doing this back propagation of the error, we are propagating it back on the edge, and then we are propagating it back here. It's on the same edge that we are again doing a modification. So we have to figure out then, how does it actually, how do we do this back propagation so that it remembers the necessary information. There are some useful topologies of RNNs depending on how you organize this. So this is one of the structures that we saw just now. There are other structures as well. So for example, RNNs can produce an output at each time step and have recurrent connections between hidden units. So in this case, that would mean, let me clear up this. The error, when I compute the error, I can compute the error arising out of this, and out of this. That is, I take the error of this, take the error of this, take the error of this, because I have the golden output at t minus 1, I have the golden output at t, and I also have the golden output at t plus 1. So I can potentially compute the error in each of these and use that error as my error to the back propagation. So there can be RNNs which produce an output at each time step and have recurrent connections between hidden units. There can be RNNs that produce an output at each time step and have recurrent connections only from the output at one time step to the hidden units at the next time step. Or I can have RNNs with recurrent connections between hidden inputs that read an entire sequence and then produce a single output. So in the last case, it would mean that I don't compute the error at all in these intermediate layers. I wait for a certain number of time steps, and the error is only computed at that place, and I don't really care what we found here, what we found here. Okay. When we talk about RNNs with hidden feedback, then we have something like this, that I have wait a moment, again my pen has disappeared, there it is. Okay, so what do we have here? This is the input layer which is feeding into this one, and there is the recurrent connection here. Then this is going into the output. This is the golden output, and here I am comparing the output of the RNN with the golden output. Okay. Now in the hidden feedback, what is happening is that the feedbacks are happening like this over time as I unfold it, and I am going to see what are the errors in each of these. Okay. Now we are not going to go into the details of this, but there is a result which says that the RNN with hidden feedback is universal, in the sense that any Turing computable function can be modeled by an RNN of finite size. Now, as you know that a Turing machine has a tape of infinite size. It's the length of the tape is unbounded. So potentially a Turing machine can keep on recording an infinite number of values. So it may put something here, something here, something here. It can keep on writing. Potentially it can write an infinite number of values or an unbounded number of values. But this is only a network with a finite number of nodes. So how can we possibly store infinite or unbounded quantum of information in a network which has finite size? So the thing that we need to focus on here is that the weights of the RNN may have infinite precision. So that means that if I look at a weight, for example, then after the decimal place there are actually infinite positions that are possible because the precision is unbounded. Now this gives me something like infinite amount of memory, and I can suitably, by modifying the weights, I can potentially keep unbounded amount of information inside this precision. So beyond this we are not going to look into any theoretical insights on how the RNN with hidden feedback is as powerful as the Turing machine. So we are not going to go into more details of that. There are also RNNs with output hidden feedback, where what's happening is that in the previous case my feedback was going from hidden to hidden, which is why we were calling it hidden feedback. That is, we were having feedback from one hidden to the hidden unit of the next time step. Here on the other hand, the feedback is going from the output to the hidden. So if I unfold it, then it's going to look like this. So it's like this, not these edges are not there. So they turn out to be less powerful than the previous case. For the hidden, as we saw, they are very powerful, as powerful as the Turing machines, but these are less powerful. But here each time step can be trained in isolation. So I leave you to figure out why that is the case. Why can I train each time step in isolation? and why could I not do that in the hidden feedback. So that's something that I leave you to ponder and find out. It's not difficult. And then, as we said, that there are also RNNs where we compute the error only at the end. So that means that I look at several time steps forward, which I do by recursively applying the transfer function to go from st to st plus 1 to st plus 2 and so on and so forth, until I reach some future state after a fixed number of cycles. It's only there that I compare it with the golden output, that is here. I compute the output at that stage with the golden output, and then the feedback works all the way back. But when it works all the way back, please again remember that these edges that you see here, these edges, they are the same edge. So every iteration, as you propagate the error backwards, it is storing everything on the same edge. But again, as I said, that edge weight has infinite precision, so potentially you can store infinite amount of information if you do the back propagation in the proper way. So we are not going to get into Boltzmann machines. I had some slides on that, but I think in the best interest of time, and we already have had a lot of topics covered in this reduced semester because of the pandemic. So we will conclude. This was just a peek into convolutional and recurrent neural networks. These are subjects on their own. Oh, just one more thing that I would like to mention before we conclude this lecture. There is a very important class of recurrent neural networks which are also very popular and widely used in practice. So let me just write it down here. So a special class of recurrent neural networks are called LSTMs. LSTM stands for long So in a normal recurrent neural network, as you can see in all these pictures, I am using the values of each layer or each time step is propagating through to the next time step, and then again propagating through to the next time step, and so on and so forth. And this works well when, as we mentioned previously, that when your decision or your output depends more on the local states. But in reality, if I look at the time steps, so suppose this is t, this is t plus 1, then dot 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 some t plus k, and then t plus k plus 1 and t plus k plus 2. Now it may so happen that if I want to look at the predicted state at this time step, it not only depends on the immediate time states in the past, which usually it will always be the case that for a dynamical system my present state will depend on my immediate past states, because that's how I'm evolving. But in some cases it may also depend on something which happened at the distant past. So that's why we need to have a mechanism for storing parts of long-term memory. Now we don't intend to store the entire memory from a very distant past. And to understand, in what way long-term memory actually influences the short-term things. A classic example is climate change. For example, when I am in the monsoon season, then the probability that it will rain today, or my prediction of rain, definitely depends on what it has been like in the previous 2-3 days. Has the humidity been rising? Do we have cloud accumulation? Is there a depression somewhere nearby? These are all local effects. But the amount of rainfall that will take place also depends on how what incidents in the past led to significant climate change. They are like long-term factors which have an indirect effect on the short-term state of affairs. Now, in order to model systems like this in RNNs, we have this special class of RNNs which are called LSTMs. In LSTMs, we have additional features to suppress the effect of some of the information. So we can have gates which kind of suppress the data from some of the past elements, and I can also decide to choose which of my present inputs I will use. So I may choose some of my present past states. So I want to deduce what's going to be what is this state, and I can use some of my previous past states, and I can choose some of my states from the distant past. So I can do that modeling in LSTM, and these are again very useful for learning systems which are dynamical, and they depend on time, and they are recurrent, but they also depend not only on the short term but also on some of the long term memory. So I think that's a lot. I have overshot my time, sorry about that. Thank you very much, and stay well.